Hello, everybody. Welcome back. Today we're going to do part 2 of section 5.2, where we're talking about logarithms, particularly the natural logarithm, and how to use logarithmic properties and how to solve equations with logarithms in it. So for this second part, we're going to need a couple of things. I'm going to flip on over to our property page. Last time we got some extensive practice with these properties where you can expand a product inside a log into two logs that are added. You can expand a division inside one log into two logs that are subtracted. And then we use this one quite a bit where if you have a power on the argument of your log, you can bring that power down. So we had some extensive applications of these three formulas last time in the first video. We're now going to get some more practice using some of these other properties. I'm going to go over a couple of them. When you're solving equations, like the good old-fashioned solve for x, we have a few tricks up our sleeves that'll help us when solving things. So let's say that I have some equation and I have on each side of my equality, I have a logarithm. If I have log base 2 of x equals log base 2 of 5, and my objective is I'm supposed to be solving for x, this property comes in handy. What it says is 2 logs of the same base are only equal if their insides are equal to each other. So like in this case, I have log base 2 here and log base 2 here, so the bases are the same. The only way this log 2 can equal this log 2 is if the insides are equal to each other. So it's almost a shortcut to solving something. If I have log equals log, then you can set the inside parts of my logs equal to each other. And then voila, we see in this case that x is 5. This is handy if we have a whole bunch of logs in our equation and I'm supposed to solve for x. If we have one log on the left and one log on the right, you can just set their inside parts equal to each other and cut out most of the problem. So this is a handy one to know. Another handy one to know are these two ones to know. We talk a lot about log base b of x. So in this case, I had log base 2. A very common, probably the most common one you'll see in this section is log base e of x. And this is one we talked about last time. That's the natural log. And so we have to remember that the natural log, which is log base e, is the inverse function to e to the x. So in this statement, if I have e to the power of ln of x, e and ln are inverse functions. So they cancel each other, essentially, and I'm left with whatever's in the power. In this case, it's the x. So if I have e to the ln x, e and the ln cancel, leaving me with just x. If I have ln of e, so the e is inside my log, again, the ln and the e are inverse functions, and I'm left with just the x part. This is a handy cancellation trick that we need. A more broad version of this is that if you have log base b of b to the x, then the log base b and the b cancels, leaving you with x. So that is to say, if I had something like log base 2 of 2 to the 5, then the log 2 and the base 2 cancel each other, and I'm left with 5. So there's tricks that we can use with our logs in order to cancel things or solve things. We're going to get some practice with this. Let's put this in motion. We're going to scooch on over to where we left off. We need to start on problem 4 in section 5.2. This is where we need to pick up from last time. Now we're in solve for x mode. Now, one other thing that we need to remember about logarithms is if my equation starts with a log, like I'm trying to solve for x and they give me a log function first, the domain of log is all positive values. I'll just put values here. So I can't take log of a negative number. So log of -5 is not allowed, for example. If we are originally given a log function to solve, we have to make sure that any x values we get are in the domain of our log. So this will come up a little bit later. We'll keep this in mind. If I'm solving an equation that originally has logs in it, I'm going to have to test my x values to make sure that they aren't accidentally bad x values. So we'll see this come up. This one it says solve for x, but I don't have any logs in it. This is an exponential. I have e to the power of x minus 8 equals 133. The domain of exponentials is all reals, so I will not have to check my x value to see if it's valid. I mean, it's always a good idea to check your answers anyway, but it's not mandatory. You won't have any dud x values out if you do the algebra correctly. So I want to solve this. And for this, we're actually going to use our handy conversion. Remember last time we practiced that if we had 8, or I think it was b to the y equals a, it transfers into y equals log base b of, oops, that was b to the y equals x. I remember it now. B to the y equals x. If we have b to the y equal x, this translates into y equals log base b of x. And we had plenty of examples of converting one state to the other, translating from one type to the other. The reason why we practice that is because it'll come in handy now. I'm trying to solve an exponential. I'm trying to solve for x, but x is in the power of that e, so it's kind of stuck up there. I don't have access to it yet. It's like it's behind a wall, behind a fence, and the e is the fence. In order to get this out from the power, to bring it down, I'm going to have to translate my exponential type statement to a log type statement, and it'll make it easier to solve. So let's retranslate this. B to the y equals x transforms into y equals log base b of x. So let's use that pattern. You start with the power, x minus 8 equals log base e of 133. So we've just translated this using this conversion formula. The power equals log base e of 133. Now, log base e, remember, is the natural log. So what we really have here is x minus 8 equals ln of 133. And our objective, remember, is to solve for x, and so I'm really close to having what x is. If I just add the 8 to the other side, I'll have ln of 133 plus 8, that's your x. And this is something that you can punch in the calculator. So here, let's show you where your buttons are. Let me dim that so you can actually see it. There we go. If you go to your calculator, you have 2 buttons for logs. This is log. Now, on the calculator, their log is always log base 10. They don't give you any options for having different bases, so you can't plug in log base 2 or something like that. So their log key assumes that it's log base 10. The one below this is ln. That's your ln key, which is the one I need here. I need ln of 133. So we're going to punch this out. We're going to hit ln, and then I'm going to put 133. Make sure that you close the parentheses. This is saying the 133 is inside the ln, like it is here. And then we would put plus 8, and we press enter. And this is what we get for our x value. In your homework, it'll tell you how many decimal places to round, but for here, let's round to 2 decimal places. We have x is 12.89. And there we go. We've solved for x. You can, of course, test this. You can try to bring your x up and plug it in here. Do we get a true statement out? Is e to the 12.89 minus 8 133? You can always test your answer. There's our x value. All right, so let's scooch on down here to my second problem. I have 2 to the 3 minus x equals 1/4. Again, I'm trying to solve for x, and again, my x is in the power of something, and I want to bring it down. For that, I want to use my little conversion thing again. That's how you bring down your power. You got to convert it. So we do the same trick. We start with our power. We say 3 minus x equals log base 2 of 1/4. So we use this conversion and we convert the exponential form to the log form, and we're here. And then again, I'm supposed to solve for x. So let's see. Let's take this x maybe and add it to the other side so that you get 3 equals log base 2 of 1/4 plus x. Now let's take this little guy and subtract it from this side. You have 3 minus log base 2 of 1/4 is equal to x. Now this is a value for x, just like I had last time. X is 3 minus log base 2 of 1/4. You can solve this. This is something we can put on our calculator. Now, as a side note, if I bring this over here, I mentioned just a minute ago when I was doing this problem that there's no key where you can put in log base 2. The calculator only does log base 10 or ln key. So how do I punch this on my calculator? Well, there's something called a change of base formula. So if you're punching this 3 minus log 2 of 1/4 in your calculator, it is the same as if you did 3 minus log 10 of 1/4 divided by log 10 of 2. So it's log of the argument divided by log of the base. This is the change of base formula. So how I enter this, I'm going to find my log key. I'm going to do log of 1/4 over log of 2. So 3 minus parentheses log of 1/4 divided by log of 2. Use that log key. I'm going to close my parentheses here and punch this out, and I get the value of 5. So x is 5. Well, that's kind of a nice looking number. Well, there's my solution. So if you're trying to plug in a log to a different base, so you do log key of the inside divided by log of the base in order to use this on your calculator. So this is how you'd punch it on your calculator. Find your log key, log of the inside divided by log of the base. All right, let's scooch on merrily along. Part C, same stuff. I want to solve for x. X is in the inside of a power here. And ultimately, again, let's see, we're going to use the same formula. B to the y equal x transfers to y equals log base b of x and vice versa. Now, in order to make this conversion useful, and again, I'll be using the same conversion on this thing, I need to have just my base to a power. In this example, I have a 5 times my base e to a power. So that is to say that I need to get the e to whatever by itself on the left. In order to convert, you got to make sure that there's no numbers hanging out in front here. In this case, I have a 5 hanging out in front. So that is to say, what I'm going to do is divide both sides by this 5 so that I get that e by itself. 35 divided by 5 is 7. So we get here. And now it's in this format where I have my base e to its power equals a number, and that's it. So now I'm going to do the conversion. I'm going to convert this into a log. You start on your power. X minus 2 equals log base e of 7. And remember, log base e is ln. That's our fancy log, natural log. And so I have this for x. X minus 2 is equal to ln of 7. If you want to solve for x, all you got to do now is add the 2 and you're all set. You know that x is ln of 7 plus 2, which you can then put in your calculator. Make sure you use your ln key, not the log key. So we're going to have ln of 7 plus 2. Make sure you put parentheses on the 7 or it'll think the plus 2 is inside the log. And we get, let's round to 2 decimal places. We get x is 3.95 approximately. All right, there's my value. All right, let's scooch on to the next one. Here's part D. And again, we're supposed to be solving for x, right? So how is this equation I'm solving different from the previous 3? In this equation that I'm solving, now I have logs showing up, which is not, the previous 3 have all been exponentials. something to a power, so your variable was in the power. This time I've got logs everywhere, so I need to change gears a little bit. Logs are not as free-spirited as exponentials are. Logs have restrictions. You have to make sure that any x I find, any x I solve for, must actually be in the domain. So I can't trust the x values I get. Like I could solve this and get x values that just straight up don't work in my logs. So we've got to be suspicious of the x values I find. They may not actually work. They may not be in the domain of our logs. So we have to make sure any x values we get don't cause me to take the ln of a negative number. We're going to have to check our x values at the end. Your x's. Make sure they work. So we got to be suspicious whenever we see a log equation. We have to check our x's, make sure that they're in the domain of our logs. So then, how do I solve this one? Now, I say this in my college algebra class. The things you want to look out for when you got logs everywhere, is every single term a log, or do they throw loose numbers at me? It looks like I have log of that minus log of that equals log of that. So anytime that I see something, it's inside of a log. So if your equation is all logs all the way across the board, then the thing that you want to set up in order to make this solve, you want to have the situation where you have one log equal to one log. That way you can use that trick of saying one log can only be equal to one log if their insides are equal. I showed you that on the previous page when we were doing the log properties. So if I can maneuver this around to where instead of having two logs over here, I just have one log here with equal to one log over there, I can then steal their insides and set them equal to each other. So that's what we're going to draw here. I have a statement of all logs. I'm going to try to squish these two together so that I have one log over here on the left-hand side. Now we can use log properties for this. Remember, if you have a log of the same base, two logs of the same base subtracted, they squish together. The subtraction makes this turn into a division. This would be ln, one log, and inside the log, the first log, its argument is the numerator. And the second log, the log that's subtracted, its argument is in the denominator. And by argument, I mean whatever's inside the log. So this one, its inside goes in the bottom. My first log, its entire inside goes in the top. And then I have this is equal to ln of 9. So I use log properties that we'd practiced in the last video, and we squish these two logs together to where it's one log with a complicated looking inside. And I have one log equal to one log. It's starting to look nice. Now, before I continue, you should look for opportunities to simplify or cancel something as I go. If I look at this log, is there anything we notice about the inside? It looks like I have a repeat factor, top and bottom, x plus 4. That cancels, and that's fine. That's legal. You're allowed to do that. You have log of whatever's left, the x plus 1 equals this log of 9 that's still over here. So cancel anything that cancels inside this big log. It might help you out a little bit, and it does here. So I squished these two logs together, I simplified down, and now I have one log with a very nice looking inside equal to the other log. Now this is where I'm going to use my trick that I talked about on the property page. If you have, that's supposed to be ln, not just any old log. That's ln of x plus 1. There we go. This trick only works if you have the same log on each side. So this is log base e, log base e. They have the same base. This next trick, we go, okay, in order for this log to equal that log, then their insides have to be equal. So this is where I'm going to steal their inside, the x plus 1 from this guy and the 9 from that guy, and say, okay, x plus 1 has to equal 9. This is our log property that we can use. Two logs of the same base are only equal if their insides are. So I just kind of bypass the logs and say, okay, that has to equal that. Then you can solve for x. So subtract the 1 from the other side. 9 minus 1 is 8. We get x is 8. Now this is where we found x is 8. We solved it algebraically. This is the algebraic solution I get. But we've got to check this 8 to make sure that it is in the domain of my logs. So if I take this 8 and I tried to like plug it in up here, does my calculator throw me any errors? So that's what I'm checking for. Does this 8 cause any errors in these logs? So you take 8 and you put it in here, you'd have ln of 8 plus 4 times 8 plus 1. That'll be ln of a positive number, which is good. So no domain restrictions there. And if you take 8 and plug it in here, you'd have ln of 8 plus 4, which is 12. ln of 12 is good. Nothing bad happens there. And this is ln of 9. So if I plugged in 8, and you could do this on your calculator up here, I would have no errors here, here, or here. So this one's good and valid, and it works. It's fine. That's your x value. Let's scooch on down to part E. Now part E, this one has logs in it again. This is log base 2 this time instead of ln. So as soon as you see I've got logs in your equation, this is where you know, okay, I'm going to have to check my x at the end. I can't trust it. Now, how is this equation different from this one? This one we said it was logs all the way across the board. Log, log, log. And so then the ticket was have one log on each side. But this one is not all logs. This is log, log, number. So I can't use this trick of setting one log equal to one log because this side isn't a log. I can't use the same trick where I had log equals log and I stole their insides. So I have to use a different tactic here. So when you have an equation with logs and a random number, what you're going to have to use is the conversion formula that we've done up here, this thing. You're going to have to convert your equation back to, so we have, that's our formula from up there. We're going to have to do a backwards conversion where we convert from a log back to an exponential in order to get this to work. So if they throw you an equation with some logs and a random number, that means you're going to have to do a reverse conversion. Take one log equation and convert it back into an exponential equation. That will help you solve it. So what you really want to do is if you have more than one log, you're going to want to squish these together, just like we did before. That's generally a good rule of thumb for any equation. If you've got logs in it, where possible, push your logs together using log properties. Condense them down. So this is log 2, this is a log 2. They are added. So the properties of logs that we'd practiced last time said if you can add 2 logs, then that means this becomes 1 log where their insides are multiplied. So there should be x times x plus 3. So this log and this log get squished together into 1 log where their insides are being multiplied together. And then I have this 2 just hanging out over here. Nothing's changing there. But what I now have is a statement that looks like this. I have a log base b of something equals a number. So I'm right here looking like this. Let's do a couple things before I start converting stuff around. Let's take this x and multiply it into that x and that 3. So that becomes log base 2 of x times x, which is x squared, times x times 3, or plus x times 3, which is 3x. So multiply the x and the 3 together, 3 times x together. And I have this 2 comes down. And if you like, in order to make this equation look more like that one, you can flip the equation, write it backwards as 2 equals log base 2 of x squared plus 3x. So now, this is my log statement. This is the conversion formula I'm comparing it to. So my 2 is in the y position. My other 2 is in the B position, and in my X position is X squared plus 3X. Rearrange this log using this conversion formula. You end up with B to the Y is equal to the inside. You have 2 to the 2 equals X squared plus 3X. So use this conversion, switch your log around into this new statement, and we get this. 4, so 2 squared is 4. 4 equals X squared plus 3X. And I'm supposed to solve for X. That was our ultimate goal the whole time, solve for X. Now, when you have X squared plus 3X equal to 4, you want to subtract the 4 over to where you have 0 equals X squared plus 3X minus 4. This here that you're looking at is a quadratic, which then you can try to solve it by factoring. Or you can use the quadratic formula, but this one does factor. So this factors into X plus 4 times X minus 1. So this is, of course, equal to 0, which then you get from this one that X is equal to -4, and from this one that X is equal to 1. So algebraically, these are the 2 values I get for X. But remember, I have to be suspicious of my X values I get, because I can get X values that are correct algebraically, but then when you go to plug them in up here, they don't actually work. So let's start off with X equal 1 and verify that it's valid. If you can have 1 and plug it up here, log base 2 of 1 is 0. So you could punch that in your calculator and it gives you a number. Plug 1 up here, log base 2 of 1 plus 3 is log base 2 of 4. Log base 2 of 4 is actually a number. And then I have this 2 over here, so we ignore it. So that is to say that 1 works. I don't have a negative value inside my log. But if I take -4 up here, and I take X equal -4 and plug it in here, what would I be punching out? I would be punching out log base 2 of -4. Log base 2 of -4. That's what I'm testing. I'm just going to take this X value and plug it in here and see if I get any errors. So when I have log base 2 of -4, remember I mentioned that when you have a base, you can plug it into your calculator as log button of the inside part divided by log button of the bottom part, the base. So let's try to plunge this in my calculator like this. Find your log key, and you have log of -4 divided by log of 2. So this is you checking your stuff. And then it says error, non-real answers. This is because you can't plug a negative number inside of a log. That's a domain restriction. That's a bad X value. So when I take my -4 and I try to plug it in up here, it's going to tell you, we got a problem here. That doesn't work. And also, when you take -4 and you plug it into this one, we have -4 plus 3, which is -1. I would again have a problem here. Log base 2 of -1 is also not doable. So X equal -4 is not making my logs happy. So I scratch it out. Now the thing is all it needed to have done was offended 1 log, and it's good enough to kill it. So I plugged -4 in up here, and it caused this log to be bad. That means it doesn't even matter if this one was good. As soon as it makes one of my logs unhappy, that's when I gotta cross it out. That's not actually going to be a valid X value solution. All it needs is to offend one of my logs, and then I've got to scratch it off. Can't have log of a negative number. So that is to say that I ultimately only have one true solution for this equation. We only have that X is 1. All right, let's scooch over to our next problems. We're done with problem 4, and now we're into some word problems similar to ones we did in the last section. So let's read them. It says, how long does it take for $3,850 to double if it is invested at 8% compounded continuously? So in this problem, they're asking about money, and they're asking about continuously compounded interest on my money. So for this, we need to recall the equations from section 5.1. From 5.1, we had two equations for interest and compounding interest. We had PERT, P-E to the R-T, where this is the equation you use when you're talking about money that compounds continuously. So I'm abbreviating continuously as CTS, continuous interest. And then you have this uglier looking formula. That's an R divided by N to the NT power. This one is compound interest. And so in section 5.1, you would have practiced knowing which formula you needed and plugging numbers in there. So based off of the wording, I've got to kind of pick off which formula I need. When I read this one again, it says, how long does it take for 3,850 to double if it is invested at 8% compounded continuously? So as soon as you see the word continuously, when it's compounded, that means that you're going to be using this formula. You're going to be using PERT. A equals PE to the RT. Once you know which formula you need to use, then you can start piling numbers into it. What are they asking me to find? Are they asking me to find a future value of money that will be in my account? Are they asking me to find what is the initial amount of money I have to put in? Or what? They say, how long does it take? Which means they're asking me to find the amount of time that it takes for something to happen. That means they want me to find t. Find t. So if I'm going to find t algebraically, that means they've got to give me values for the rest of the letters, right? They got to give me R, they've got to give me P, they've got to give me A. So let's keep a running list. 3,850, what is it? It says, how long does it take 3,850 to double? So 3,850 is the amount that I'm starting with. That's the principal. That's how much that they're going to invest originally. And what would be my future value? What future value are we wanting to have? It says I want 3,850 to double. So that means my future value A has to be twice as much as my principal. So we just multiply it by 2. They want the future value to be 3,850 times 2, which is 7,700. So my future value, we want to know how long does it take for the future value to be 7,700. And my interest rate R is 8%, but make sure you convert that to a decimal by dividing by 100. You get 0.08. These are the three values I know. Let's bring them over and pop them in my formula. 7,700 equals P, which is 3,850, E to the R, T. Now I'm supposed to solve for T here. So for this, I'm going to have to rely on some of the solution techniques we just finished talking about. Let's first get this E by itself. That's always the first thing you want to do. Get E by itself. So if there's a number in front of the E, you need to divide it away before you can do anything else. So you have 3,850E divided by 3,850, that cancels, and I'm left with the E on this side. And on this side, 7,700 divided by 3,850 is 2. So I get here, 0.08 T. Forgot to write my T right there. This is my statement, and I'm supposed to be solving for T. Now for this, I have an exponential form, and I have my variable inside the exponential. So for this, we do our little conversion thing. B to the y equals x converts into y equals log base b of x. Now, one easy way that I like to think of the conversion that kind of gets around having to use this a little bit is that this is E. And I want to get rid of the E so I can get at the T. This E is kind of like a wall in my way. So if I want to get rid of the E, what I can do is introduce the inverse function that would kill it. So the inverse function to E is ln. So if you take the ln of both sides, you end up with ln of 2 equals ln of e to the 0.08t. So what happens on this side is when you take the log of both sides, the ln of both sides, the ln and the e cancel because ln and e are inverse functions, and I'm left with the 0.08t equals ln of 2. But what we've basically done is we've done this rearranging. Y equals log base e of 2. Y equals log base e of 2. We've done this conversion, but we've disguised it in this, inverse function type argument. I like to do this personally. It seems a little quicker in my mind than doing this mental conversion. So I think from here on, I'll use this trick. But what we're actually doing here is converting this exponential form over to the log form. We did it here. All right, let's solve for t. If I'm going to get t by itself, all you got to do is divide both sides by 0.08. We get t is ln of 2 divided by 0.08. So let's use our calculator here. Find your ln key down here. ln of 2 divided by 0.08. You get t is 8 now it says round to 2 decimal places up here in the directions, so we're going to do 8.66. So it takes 8.66 years for my principal amount of money to double if invested under these conditions. All right, let's move on to number 6. We're moving merrily along. It says 8650 is invested at 5.5% compounded continuously. So before I read the rest of the sentence, I know that I'm going to use the continuous interest formula. I'm going to use PERT for the rest of this. Now let's read what it wants. It says, how long will it take for the balance to reach 25,950? Round your answer to 2 decimal places. So when it says, how long will it take, they're asking me to find a time. So that means they're wanting me to find t in this formula. So if I'm going to find t, logically that means they have to tell me what r and p and a are. So what is my principal amount of money that I'm going to be investing? I'm going to be investing the 8,650. And they told me they want a certain future amount. It says, how long will it take for the balance to reach this? So this is my future amount of money that we want in my account. So we want A to be 25,950. My interest rate R is 5.5%. Convert this to a decimal by dividing by 100. So we get 5.5 divided by 100 is 0.055. So this is the value I'm going to use for R. Take all these values, and pop them into my formula. You have A, 25,950, is equal to P, E to the R, T. Now we're going to do the same exact solution process as we did last time. We're going to get the E by itself by dividing by 8,650. So I get E to 0.055t equals, so let's divide here, 25,950 divided by 8,650 is 3. Well, that's nice. And then I want to solve for t. But before I can get at the t, I've got to get rid of the e. So for that, I'm going to introduce the inverse function ln. So I'm going to take the ln of both sides. The ln and the e cancel, and on the right-hand side, I'm left with 0.055t is equal to ln of 3. Now, I did this cancel policy, but what I've really done is use that conversion formula and converted the exponential to a logarithm, and I get here. Solve for t by dividing by 0.055. And we will round to 2 decimal places, it says. ln, make sure you use your ln key and not the log key. ln of 3 divided by 0.055. You get t is 19.97 years. So it'll take just shy of 20 years for my principal amount of money to grow to $25,950 if invested under these conditions. All right, let's scooch on over to the last one, number 7. It says, if $6,000 is invested at 7.5% compounded monthly, how long will it take for the balance to double? Now, just like last time, you have to choose which interest formula you need to use. Now, since this is compounded monthly instead of continuously, that means that I have to use the compound interest formula. That's the uglier looking one. That's A equals P 1 plus R divided by N to the NT power. And they're asking for me to find how long it will take. So again, I have to find T. So logically, if they want me to solve for T, they've got to tell me what N is, R, P, and A. They have to tell me all the other variables. So let's make a list. What is my principal amount of money that I'm going to invest? It looks like I'm investing 6,000. And what is the future amount of money that I want to have in the account? It says that I want the balance to double. So that means the future amount of money that we want to see in the account at that time is $12,000. The interest rate R is 7.5%, which you then divide by 100 to get its proper decimal value. R is 0.075. And what else? I need to know what N is. Now, in this formula, N is the number of times per year the interest is compounded. So if it's compounded monthly, that is 12 times a year. So N is 12. Let's pile all of this into my formula up here. We have A, which is 12,000, equals P, which is 6,000, 1 plus R over N to the NT power. Now I'm trying to solve for T. And again, I have T is in the power of something. And so this is acting like it's in my way. And I'm going to have to try to solve here. Now, let's put things into perspective. This is 6,000 times this. Now, I have 1 plus 0.75 over 12, which means this is in the parentheses is some number. This is going to be some number raised to the 12t power. Now, this number is not e. So it's not like this is e to the 12t. This is some other number to the 12t. I'm going to have to introduce a log, just like last time, in order to solve this thing, but it's not going to quite work out as smoothly as it did the last time. Let's work through it. Just like in the last problem, what did we say? We needed to get e by itself by dividing by the number. Well, this time I'm going to get this disastrophe by itself by dividing by 6,000 on both sides. So you have 12,000 divided by 6,000, which is 2, and that's equal to this part that's left, the 1 plus 0.075 over 12, the 12t. So this is kind of similar to what I had last time. Instead of 2 equals e to whatever, I have 2 equals this mess to whatever. But I am, just like last time, what I'm going to do, this is what you should do, you should still take the natural log of both sides. But here's the kicker. Because this is not e, the ln and this doesn't cancel, right? Things only cancel when you have an ln and an e here, but this is not e. This is some other mess. So nothing cancels here, unfortunately. I am stuck leaving this as ln of that to the 12t power equals ln of 2. But what you can do, now that you've introduced logs, and this now is a logarithmic equation, that you can use log properties to your advantage here. What I'm going to do is, since this 12t is a power on this argument of my log, this is like saying ln of all of this mess, I'm going to use log properties and bring the power down, just like that we did last time when we were practicing log properties. You can bring powers down and put them in front of the log. That's algebraically valid because logs are kind of quirky that way. That 12t, it plops down like that. And I'm trying to solve for t, right? I'm trying to get t isolated. 12 is just a number, and technically so is ln of this. This is something I could punch on the calculator and get a decimal for. So I'm going to solve for t by dividing by the 12 and dividing by that ln. So divide both sides by the 12 and that ln of all of that. There we go. So that cancels, that cancels. So t is that mess. ln of 2 divided by 12, ln of 1 plus 0.075 over 12. Now that's a mouthful. You have to be careful punching it out, but when you're done with that, you'll have t. We're going to round to 2 decimal places, just like we've done before. So let's be careful here and punch this out. I have ln of 2 divided by, big parentheses, 12 ln 1 plus 0.075 divided by 12. So I put parentheses around the fraction, another set of parentheses to close the parentheses on the ln, and then one more set of parentheses around the denominator. So we get here. T is approximately 9.27. So it takes about 9.27 years for the principal amount of money to double if invested under these conditions. So it was started out here. I'm trying to solve that. You take the ln of both sides and you get there. And unfortunately, you can't cancel the ln of that because that's not e. But what you can do is flop that 12t down in front, which we did there, and then divide both sides by the 12 and the ln to get the t, which is what we did there. Punch it on your calculator, making sure to use your ln key and not the log key, and you should be all set. Okay, this is the end of section 5.2, where we've talked about log properties and how to solve logarithmic equations and exponential equations. So I will see you next time.